All right, let's start. Do you have any questions? All right. So remember, midterm one is next Monday, right? In person. So bring your laptop, right? There'll be coding component. You need to do live coding. Make sure your Python is working. All right. Everything is functioning. Okay. So there's no question. Let's kind of pick up from where we left off last time. So where we were last time, right, was we were in the middle of discussing the transition from the so-called physical model, right, to the risk-neutral model, right? Or, well, really, I mean, you can call it model, but it's really the same, the same stock. So maybe it's more like a point of view, right? I mean, you can use the word model, but I would say that might kind of give you, some misconception. So you can call it point of view, right? Like that. So basically, right, to emphasize, right, and this is exactly why this term right here is the same old stock, okay? It's not like we jump to a mystical universe and see a different stock, right? The path is the path. The coin is the coin. It's just that we look at it, right? We would like to look at it from a different point of view, right? We would like to look at it, right? So right now, right, when we write something like this, both of these supposedly will be under P, right? Under the physical probability, under whatever that our current world is observing. So we want to find, right, another point of view, right, the so-called risk-neutral point of view, so that, right, I guess I should write it the other way. I'm not used to that. Is a Brownian motion, right? And of course, once we do that, we can call this W tilde, right? So, well, and again, right, the point of the lecture last time is to convince you of why, right, or what's the reason why we want to do that, right? It has to do with the whole risk neutral pricing framework. But anyway, right, so the abstract question, right, the general question then is, okay, for any theta. In fact, it's even more general than that. The most general version, I guess, is when this is a function of time. You don't have, so, notice that here I'm still writing it as a linear, right, function, because this is a constant times t. That's because, that's what we're dealing with anyway, right? But the most general version, who knows, it could be get more general, but as far as I know, the most general version, right, would allow you to get this as a function of t under some condition, as Cesar would would love to tell you, right? Go ask it. But I would just want to discuss this, okay? And anyway, so notice that then in this sense, right, the Brownian motion is sort of like depending on theta, right? Because you get to choose your theta. So some version you can call theta here. The only theta we're interested in is this one. So, again, right? Like I said, I'm more interested in the meaning of the math rather than the technicality itself. But there's some technicality we want to discuss. And so, right, so actually, the result to tell you how to do this is exactly the so-called Kusanov theorem, right? again, I'm just stating it in this context, and you can go find out about this whole, glorious detail somewhere else. So Gasanov's theorem would tell you something like this. So first of all, right, do remember that we also spent some time last time to discuss the idea of a change of measure, right? So you can define a new probability, right, measure by, right, using a change of measure kernel that satisfies, right, two things. That is, has to be positive. Well, technically speaking, it's just this, and the expectation, right, is 1. Okay. And again, right, do remember that I kind of skip a lot of things here, but the way we do it like this means that we define P tilde, right, on the most general filtration we have in mind, which is, right, the biggest filtration in the future, right? I mean, right, you could potentially extend it further, or you can extend it back, whatever, right? But here, I guess we have the option pricing framework in mind, where, right, we just define it on the biggest filtration with the most events, and then everything goes backward from there. Anyway, right, so this is the general change of measure framework, nothing fancy here. The punchline, right, is what is this guy? What is ZT? So ZT here will be, I'll just write EXP here, right, minus theta times T minus 1/2 theta square. Whoops, I'm not functioning very well. Minus W theta times WT minus 1/2 theta square times T. All right, like that. And I'm still missing something. It's a big T. Like that. All right. Okay, so again, right, this is probably the sloppy way to state Gasanov's theorem. The point is this, right, that basically if you were to use this, right, under this understanding of the change of measure framework, then, right, the new Brownian motion, the new process you define like this, which is, right, by the way, this is called Brownian motion with drift, right? This is a Brownian motion with drift under the original probability. This guy will be a Brownian motion, right, under P tilde. Is that okay? So that's the result. If you use this change of measure kernel, then W tilde will be a Brownian motion under P tilde. So basically, right, the message more or less is you could, right, get rid of the drift, right? A Brownian motion with drift definitely is not a Brownian motion, but you could find a new point of view so that that Brownian motion with drift will become a Brownian motion under your new point of view. All right, any questions so far? So, right, we'll spend some time trying to explore why this is true, right? Why this is true mathematically. So there are many details, right, to come up. So the first one is just some kind of connection, right, between P and P tilde. Remember that it will come out of this Gasanov's theorem as well. But even, right, from the pricing framework, we would like, right, even though technically speaking, P tilde and P doesn't have, any deep connection, the one thing that at least, right, we would like to have is, gosh, it's been a while, I forgot already the notation, but something like this, all right? I'm not sure if this is the right one anymore. But basically, these two guys have to be equivalent. But equivalent doesn't mean that, they're equal. It just means that any event, right, that is impossible under one point of view would be impossible under the other point of view. All right. So this, again, it will come out of Gasanov's, that's what we'll explain. But it is desirable, right, from a risk neutral pricing point of view, to prevent arbitrage, right? Because you know that, again, we won't go into much deep details here, but you construct a risk neutral pricing framework, and then you show that there's no arbitrage opportunity, okay, under the risk neutral pricing framework. So that's fine, good. But someone can ask, right? Okay, that's a fictitious point of view, right? We usually view things under the physical point of view. It could be that I can still construct, right, with whatever you price, right? I can still construct a arbitrage opportunity from, right, the physical point of view, which is, right, all that matters to us, because that's where we live. That's where we live. Then, right, that's no good, because your no arbitrage conclusion is of no value. But this, well, prevents that, right? Because if there is no possibility of arbitrage under the risk neutral framework, that would translate to no arbitrage opportunity, right? Under the physical framework, right? And A here, right, in this case will be the probability that you earn money without risk, right? The event that you earn money without risk. Anyway, right, so why would this be true, right, under the choice of the change measure kernel? So by the way, first of all, right, I hope it's trivial that these two conditions are satisfied, right, by this choice. By the way, right, this by itself is a independent change of measure framework, meaning that you can choose any change of measure kernel that satisfies this condition, right? Anything like this would make sense, okay? By the way, if you allow 0, that's actually will make some of the event not equivalent, because if you allow ZT to be 0 under some event, that would mean, right, that the event that might not be 0 under P will be 0 under P tilde. So that would make it not equivalent. But here, right? So first of all, I think it's clear that with the choice of the choice of the kernel like this is strictly positive. And, right, the expectation is 1 from what we know from the Brownian motion, right, property. So here again, right, when you deal with this thing, pay very, very special attention to whether you're looking at E or E tilde, okay? It may be confusing. Also, whether or not you look at W tilde or W, all right? It really means different things. So first of all, this is trivial, right, by our choice. And second, right, like I said, the fact that ZT is positive allows this to be true. Why? Because suppose, right, I mean, I'll just do one direction, you see, right? If A, such that, right, P of A is equal to 0, right? Then P tilde of A by definition is expectation, right, of ZT indicator function of A, right? Now, if P of A is 0, right, then the indicator function of A will be 0 almost everywhere, right, under E. Therefore, right, this expectation doesn't matter what ZT is, will be 0, right? So that's fine. Conversely, right, suppose P tilde of A is equal to 0, right? What can we do? And actually, that's the rub, right? Here, notice that when we go forward, actually, we don't use anything, right? I mean, we don't use ZT positive here at all. As long as A is an event that has probability 0, then this whole expectation will be 0. The converse, though, right, is what if you start out with the risk neutral side, right? Now, the thing is, notice, right, that because if ZT is positive, that allows you to do the inverse, 1 over ZT, right? So actually, because ZT is positive here, it allows you to do the other way, meaning that you can write P of A or expectation of a thing. So conversely, you can do this. All right. You could do this because ZT is positive. So 1 over ZT would make sense everywhere, right? If there's some point in ZT is not equal, is equal to 0, then you cannot do this. But exactly, that because ZT is positive, right? The it basically means that you can change measure forward and backward. Okay, so there is a kernel that allows you to go back, which is exactly 1 over ZT. Okay, and therefore, right, exactly because of this, right, and 1 over ZT like this, right? So basically that means P of A is, right, expectation tilde of 1 over ZT, indicate function of A, that would be 0. All right, so that's just a quick remark on how, right, this choice guarantees that the two probabilities are equivalent. Any questions so far? Okay, so that one is actually an easy one, right? Now, what's the punchline, right? The punchline is W tilde T, right? Which is WT, right, plus theta times T is a Brownian motion under P tilde. Okay. Now, again, this is not a very difficult thing to show once you know what you're doing. But let me explain to you how it can be a very, very complicated thing to think about if you're not familiar with this. The reason is this, right? What does it take to show this? Well, again, right, assuming you don't know some fancier detail, not fancier, another nice point of view about Brownian motion, then I assume that you have to go with the checklist, right? You have to do the following. Right? So now, what do I want to say here, right? So first of all, right, also try to appreciate a little bit. Is this true? Well, that's true because, right, at 0, this is 0 and this is 0. So this choice of function also matters, right? If you choose a function such that it's not 0 at 0, like a general drift, then technically speaking, this can still be a Brownian motion, but it doesn't start at 0, right? So here, though, right, because our choice still starts at 0, so that's good. What about IID increment? Well, you change probability, right? Again, maybe because the drift, right, the drift is deterministic. So you may believe that it's still independent, right? It still has independent increments. But be careful, right? Maybe it's kind of clear that this guy has independent increment under P, right? Under the physical probability. Because, under P, this guy is still Brownian motion, right? So this guy is deterministic, so it should not affect anything about the independent increments. But when you switch to P tilde though, right, then it's unclear whether or not WT itself still maintains independent increments, right? Remember, right, the idea of increments is actually not that straightforward to check, right? You need to look a little bit carefully into it. So that's, let's say, a question mark. The last one is also a question mark, because now you have to deal with, right, the distribution under, so again, right, let me say this. The punchline is they're all under P tilde, right? You're not looking at them under P, okay, under P tilde. So let's just demonstrating, right, how this can be, not very easy to look at if you don't know what you're doing, is, for example, right, I demonstrated last time, how would you do something like this, right? For, again, right, if this guy has any hope of having of being a Brownian motion, then this better be 0, right? This better be 0. But let's see what it takes to compute this. Well, it's not that straightforward, right? Because all you can do is rely on definition, right? Relying on definition. And that's the only thing you have. And by the way, right, you might realize that worse yet, say we're looking at little t, right? This is for any t between 0 and big T. Okay. But the change of measure, right, framework only tells you about big T, which again, right, I explained why. Because this means that you define everything on big T, right? For X is adapted to the biggest sigma algebra. So if this is defined, then it should be defined for everything that is on F little t, because F little t is contained, right, in F big T. All right. So what that means is you have to just follow the blueprint. And let's say you do this, right? So you first of all, you do this, let's say, right? That's by definition. And then you plug in what these guys are. So that's WT, right? Plus theta times T, right? And then you have e to the, minus, right? Theta times W big T minus 1/2 theta square times big T. And you want to ask if this is equal to 0. Okay. And right, let's just say that's you again, right? If I give you 5 minutes, I hope that everyone can calculate this out, right? And check that's equal to 0. But you see that, right? First of all, that would give you a pause, meaning that you want to think about a little bit. And second of all, right, that's just a trivial check within this big list of items to check, right? Because checking that, suppose that it checks out, that doesn't mean anything, right? It checks out, that means that you don't negate this, but that doesn't mean that the whole thing is true. So, right, what I want to tell you is that this checklist is cumbersome to do, okay? And it justifies using a nicer way, a different framework to look at Abraham motion, all right? And so the nicer framework I'm referring to is the so-called the martingale characterization of Abraham motion, all right? And this is one of the places where I think the martingale framework is really nice. It says that, right, some process, you don't know what it is a martingale, is a Brownian motion, right? Of course, here, with respect to some filtration, under some probability measure, right? Whatever. If and only if. So we suppose it starts at 0, right? That's just something that has nothing to do with probability. It's just where you anchor the process. But the second one will be interesting. It says that the exponential martingale process associated with W, namely this, is a FT martingale for any, right? The emphasis is any theta. All right. So this right here, right, is a deep detail that we want to look at. What does it say, right? It says that instead of checking all these requirements, right? Again, the first one is whatever. All we have to do is look at some exponential process associated with that proposed, process, and make sure that it's a martingale for any, choice of the parameter we plug in, right? Now, if you know your probability theory, then you would see where this comes from, or at least you would see the correspondence between this and another technique, right, in probability? Does this remind you of something that we like to do in probability? And actually, that's the key to this whole idea as well. So by the way, right, what is martingale all about? Martingale, right, might seem fancy and stuff like that, is about expectation, right? Now again, I think at least it might have been drilled into you that conditional expectation is not the same as expectation, which is true. But another higher point of view would tell you that essentially conditional expectation is expectation, meaning you are taking an average. You just have to make sure that what kind of average you're taking expectation with respect to. So the point of view here is that you trade a characterization via distribution into a expectation check. All right. And again, right, expectation is always easier to do than distribution, because distribution means that you have to check a lot of details, while expectation means you only have to perform one calculation. All right. So any framework from probability that has that kind of taste.
Is this similar to when we check like the moments or the characteristic functions?
That's exactly it. This is exactly the moment gen function idea. Yep, that's exactly it. And as you will see, this is nothing but a generalization of that idea. All right. So let's try to explain why. So yeah. So let's take a look at the reason, right? So first of all, let's take the direction forward, which I would claim is easy, right? Meaning that if you know something is about motion, then just do your calculation, right? This is clear. All right. It's the backward direction, right, that we want to look at. Okay. Meaning that when we have something like this, how can we claim, right, that something is a Brownian motion? This guy is a Brownian motion. And so, right, what do I want to say here? Then, right, if we want to propose a new idea, then the only thing we can say is that it matches, right, the old idea. Meaning that we need to check that this guy has independent increment and is a normal distribution, right? The increments. So let's see, right? So what do we have to work with? What we have, right, is that this guy is a martingale, right? Meaning that expectation of, right, e to the theta wt minus 1/2 theta squared t condition on fs will be e to a theta ws minus 1/2 theta squared s, right? This is true for any s less than t. That's what we have. Now, what do we want to conclude? That wt minus ws is independent with respect to the filtration fs, and wt minus ws is normally distributed. All right, is that clear? That's the backward direction. Now, tell me, can you see how we can go from here to here with what we have? Again, if you're not used to this, right, it might seem strange, but it's amazing enough that you just have to rearrange term. First of all, right, I mean, WS is adapted, right? W is adapted. That's my assumption. I mean, at least it must be adapted. Otherwise, I won't even look at it as a ground motion. So it's adapted. So I have this, and then I have this. Okay, so that's what I have. Agree? So that's just another way to write this. On the other hand, this is all I need. Why? First of all, right, here, stare a little bit. It says that when you take conditional expectation of this guy under Fs, all you get out of here is constant, right? There's nothing random on this side. Now, of course, if you do it with one particular theta, for example, theta equals to 1, then not much you can conclude. But if this is true for all theta, right, that's the key. Then, first of all, you can conclude, because the right-hand side is not random, that this, like, so basically you're saying that taking conditional expectation is like taking expectation, right? But again, emphasis is true for all theta. This allows you immediately to conclude that WT minus WS is independent with Fs. Is it clear so far? Right, we can elaborate more on this idea, but that's the essence of it. That basically, because the right-hand side is not random, right? Notice that if you take conditional expectation, usually it must come out as something, right, random, depending on Fs, right? But here it's just a constant. That means that doesn't matter how you change theta. The conditional expectation does not depend on Fs at all. So that means it's independent. But then, right, then you're home, because then you can drop the conditional expectation. And what do you see? You see the MGF of a normal 0t minus s. There you go. Yes and no, right? By the word there. What there? What there are there? you mean two, right? You need two. So yes, your idea is correct, except that you need to know what they you're talking about. If you mean by there, you mean WT and WS. Oh, yes, that's correct, right? That's good. So exactly from here, you just said the next step of this problem. If you want to carefully show why this is true, you could do something like this. You can show that this, right, let's say star. Star would imply that for any, let's say theta 1, theta 2, right? You need to be careful here. Then expectation of e to a theta 1, WT minus WS. By the way, WS is not enough. You need, like, any WR less than S, whatever. The technicality just kind of gets boring. But what you say is almost enough. Will be this. Yeah, this is called a joint moment change function. You're absolutely correct, right? So that's exactly the next step. That somehow, right? And I hope you can see how you can do this, right? By leveraging this conditional expectation. But you can show that. Okay, and that's exactly the independence. That's correct. Okay. Any questions so far? All right. So this martingale, right, representation, martingale characterization of a ground motion, or actually of a process in general, it can be generalized to a more theoretical level. Admittedly, unfortunately, it's really an academic concept, right? It only is useful when you are working under, like kind of martingale theoretical framework. But it's really powerful, all right? It's really nice if you want to deep down understanding of, what you're doing when you kind of do some change of measure, or, you are characterizing a process or something like that. Okay, so how does this help us in our quest, right? So remember, so back to our goal, what do we want? We want to show that W tilde, right, is a P tilde run motion. So now, right, with the armed with the martingale characterization, you could see that we can simplify our problem like this. We can show that e to the theta, right? It might be confusing because we have already a theta right up there for the definition of WT, right? W tilde. So, well, I don't know. Let me change to some parameter, sigma, right? E to sigma W tilde T minus 1/2 sigma squared times T, condition on Fs, right, will be equals to the sigma W tilde S minus 1/2 sigma squared times S for any S less than T. Need to show. Right, and then any sigma. All right. Meaning that if we can show this, then we will have a conclusion that this guy is a P tilde prime motion. Is that okay? Is that clear? So that we reduce our problem to that. Okay. Any question? Now, the next thing, right, is that I'll just this right. It's just really a cosmetic change, and there's something to it, but I can do this, and I'll let you think about it. This is very easy. It also is equivalent to for any big T that's fixed, right? This is my horizon. This is my exploration. I can show the same thing, but with big T here. Is that okay? So instead of proving it for any moving S less than T, less than big T, right? 0, that kind of thing, I just fix a big T and prove it for any moving little t. It's the same. Okay. Why is it more convenient here? Because my change of measure kernel is defined for big T, right? I mean, so it's easier that way. But they're the same. All right. Any questions so far? All right. Now that said, though, right? You should notice that it's not that straightforward. Even though I claim it's easier, which it is, right? There is still one last hiccup. The last hiccup is, what is this guy? Right? What is this guy? I mean, how to compute. Because notice, right, for all you know this. Oh yeah. I mean, we don't do anything fancy about infinite sigma algebra for T-main. And even that, if that's the case, I think you need to assume some conversions or something. Otherwise, right, you can't talk about infinite. So yeah, finite. But I mean, like, again, right? Just think of it as option pricing framework. I'm not discussing general math. The reason is, right, any option pricing framework, you definitely will have a finite horizon in mind, and you go backward, right? You never really go to infinite. I mean, unless you talk about perpetual option, but those are more, for theoretical, entertainment rather than real life. Okay, so right back to here, right? That what do I want to say here? Yeah, right. the definition does not take care of this, right? Or I mean, maybe it does, but you need to somehow imply that, right? So what does it mean to, or how do you relate? So I guess that's the question, right? How do you relate conditional expectation with under P tilde with, right? Obviously, right, it will be conditional expectation under P, right? So this is for X and Ft, right? So first of all, right, maybe for the one that's kind of the brave ones, right, among us, you know, it should work in the same way, right? I mean, why not? If expectation works like this, conditional expectation should also work like this. What do you think? True or false? And how do you know? Should the formula work in the same way under conditional expectation? Well, you know the answer. All right, but let's take back right to a more innocent mind who just saw this for the first time, right? Then would you be able to believe this formula, or would you be able to think your way out of it and see that it may not be true? And by the way, when you say divide by z little t, you already assume, right, that z is a martingale. But the change of measure doesn't have to require that to begin with. Anyway, I mean, I think you know the answer, but I'm asking, right, because again, right, if you know the formula, you are not really thinking through the process yet, right? So just play innocent here, which is a decent question, right? Can this be true? Why not? Anyone?
I think not, because Z of capital T, that's defined on the filtration of capital T, right? So
Sure, but I don't hear an explanation, right? Or if you say that, I mean, you're just repeating the property of Z, right? What Z big T, right? Why does that mean that it cannot be true? So let me tell you a little trick, right? Which is very, very powerful in math. I mean, in real life too, I think. You want to check out, right, whether something is true or not. Try a few examples, right? Why not? That's getting your hands dirty, right? If check is very useful in many ways. First, when you try out a few examples, you understand what the formula or principle is trying to tell you, trying to propose. And second, right, you can check if it really works or not and how the working looks like, right? So try examples. Just try examples. Bring things down to the concrete level. Don't stay abstract for too long, right? So how would you concretize this kind of question? What kind of example would you use? Hmm. Any example to use? How about this? Then what's the left-hand side? What is this? Of course. What's the right-hand side? Well, you don't know what it is, but it will be a random variable, right? It will not be a constant. Agree? I mean, if z is some random variable, which, right, which is what we assume it is, then it cannot be the same. And this is enough to show that there's something wrong with the formula. Is that okay? And actually, funny enough, this might propose a fix as well, right? So how should we fix the formula? At least to make it work for this case, for this so trivial example that we picked. How would we fix it, at least to work in this case, right? And maybe with that fix, it can work in general, who knows? Again, right, this is the power of thinking example. How would you fix it? You would fix it by dividing by that quantity, right? Notice then it at least will pass my trivial example, right? Of course, whether it's true in general is, what we need to investigate further, but at least, right, you can see a way to make it past this, right? And it turns out that exactly this is the case. Now, right, for our particular construction, right, of z big T, then we can define as z little t, right? Okay, so far, any question? So this is the true formula, right? But again, I want you to appreciate why, right? The formula must be this way and not a straightforward application or expectation, right? So in this sense, expectation is different from conditional expectation, but it's still essentially expectation, right? So yeah, I mean, this lecture is very, very mathematically heavy. We just pull probabilistic theory, right, from right and left. But once in a while we should do that. Any question? So right now, how to prove this? Well, what is it? Yeah. So to prove this, right, then you need to understand what constitutes conditional expectation, right? So because if you don't understand what conditional expectation is, or rather, right, here it doesn't really matter p tilde or whatever. Suppose I have a random variable and I have a sigma algebra. What does it mean to take conditional expectation? And here, right, I would definitely test your education from Casper, right? He definitely would have taught you this, I'm pretty sure, but can anyone tell me what is conditional expectation? It's not an easy concept, by the way. It's rather intricate, and normally I wouldn't even care, but here we definitely have to use it. Anyone knows? There's a technical definition that we'll use for this problem, and there's an easy way to think about it, which is also nice that you should know. And conditional expectation is used everywhere, right? Not even in our context, so you need to know what it means. Anyone? Not bad, but you didn't capture everything yet, because what does that estimation have to satisfy, right? Because I could say, well, I estimate everything with expectation. Isn't that a way? Does that make sense? So yes, what you say makes a lot of sense. It's an estimation. That's true. But I could say that, well, so I just do this, right? You say estimation, right? I will estimate like that. So there's more to it, right? What does that estimation have to satisfy? Right. So first of all, right, it should be is a random variable that is in the F little t sigma algebra, right? So it must be based on the sigma algebra. but that's not it, right? What else do we need? So let's call this, just give it a name because we will do something with it, right? What does this do? So first of all, right, like we said, it must be based on the sigma algebra, right? But second of all, it will be the best mean square estimate, keyword mean square. So it has a lot of connection with regression, actually. Regression, you can look at some framework regression is really conditional expectation. All right, what does this mean? This means that if you propose any other guess, suppose you propose any other z, all right, then I will know that the mean square error for my estimate based on y, which is this conditional expectation, will be less than. Okay. So it's literally a projection of this random variable onto this filtration, this sigma algebra. All right. This is a square inside expectation, all right? So this is a mean square error of the estimate. So this is a residual sum of square kind of thing. Now to make it more concrete, because maybe you are not used to sigma algebra. Sigma algebra again also, oh my gosh, somehow my things, no. Gosh, 1 second here, my Apple Pencil is not responding. Right. Sigma algebra, right, is also a very, very easy, not easy, but very natural concept, but you need to kind of think your way out of it. But you say more concretely, it's like this. Suppose you can do this, right? Try to think more concrete if you can. Basically, suppose I condition on y, okay? Let me say on v, let's say, let's not make it confusing for you. So v is some good old random variable, right? I want a condition on, right? This is what probably you will see more in the lower probability context, right? You would have two random variables, right? That has some joint, and you want to find condition one or the other. And you would do something like, you would have the joint density, and then you would divide by, x, right? Well, maybe let me just do u then, right? You would do this, and you would do the marginal, right? Like this. So that's exactly f of u condition on v. So, you would do something like this, integral of u, like this. All right. So you might something like this. And actually, if you do this, you have this little funny notation like this, blah, blah. All right. But so there's that way. And actually, it's exactly this way too. But let me tell you that, right? If you condition like this, right? Which, by the way, can be viewed like this, because you can think of the sigma algebra here. It is generated by V, right? Again, Casper should have told you what it means. Not super important here. But what it means is, right, that from our point of view, more generally, right? Notice that this point of view is not that bad. It's just very concrete, too concrete for use, because a lot of things in real life may not have joint density, right? What if one is discrete and one is continuous? Then they do still have joint, right? But that is not going to be a joint density, right? Because one is discrete, So again, this framework this way of looking at things not bad. It just doesn't capture, it's not flexible enough. So here, right, we will say that conditional expectation, right? What do we mean by saying this is in FT now? What it really means is just going to be a good old function, some function based on V, right? So first of all, conditional expectation on some random variable means that you must base the estimate on this random variable. Furthermore, right, the mean square estimate still holds. The best mean square estimate still holds, meaning that for any other, let's say, function based on V, you cannot do better, meaning that the mean square error using this guess is the best. Is that okay? So it's exactly the projection of U on V, right, on the space spanned by V. Just pay attention that this doesn't have to be a linear function, all right? This doesn't have to be a linear function. It depends on how U and V interact. But if U and V have joint normal distribution, right, or multivariate normal, then this will be linear. And that's why linear regression, right, always like to assume normal noise because, you know, that just fits right in. But okay, so there's that. That's kind of a quick and dirty explanation of what conditional expectation means. Have you heard of this from Casper? You should have, right? Did you? Or I mean, maybe not the best mean square estimate sense. Did you hear from this before? You know this or no? Yes, no? Don't remember? That's okay. All right, again, it's very, very useful, trust me. Actually, let me tell you something right away that's how useful it is. Maybe this is a silly question, but what is expectation? Again, right? I mean, I know what expectation is, but do you think it has some meaning besides some kind of calculation you have to do? Sure. Meaning, average value, right? I mean, anyone can come up with some kind of average value, right? What does that average value do? So here, again, my question might seem a little strange if you don't know where I'm going. But first of all, right, at least I hope you know this, right? If you condition on the trivial filtration, then it's really expectation, right? That's clear, right? This is usually F0 right there, right? So you could really use the top framework. So what it really means, and I bet some of you may not know this, or maybe all of you haven't known this, which is fine, is that your expectation, right, of course, is the best mean square estimate, the best constant mean square estimate of X. Meaning what? Meaning that for any constant, if you look at the mean square estimate using the expectation, it will be always smaller. So you can make up a silly story, a silly game like this, right? You have a random variable, you ask your friend to guess, right, the value of that random variable, and they will have to pay, right? It's a, I don't know, a punishment. They have to pay, right, based on their error, right? And if they have to do this a lot of times, right, I guess on the square of the error, right? What's the best value they can guess? The best value they can guess for this game where they have to pay for playing this game is the expectation, meaning they will pay the least cost if they guess it that way. Okay, so expectation has that meaning too. Did you know this before? Anyone know this? I will take that as a no. Oh, cool, awesome. That's good. Roger, I would have told you this. Cool, awesome, right? So, but you see how, right, exactly this fits in the top framework, and that's exactly how, right, expectation, conditional expectation is like expectation, right? Conditional expectation really is a generalization of expectation in the right way, all right? So because it's still projection, right? Expectation is projection into the trivial filtration, sigma algebra. and conditional. Yes, I'm not using that. I'm using the mean square error as a criterion. So I'm using the L2 projection as in the definition. All right, that's the if you want a technicality. I'm using the L2 projection, right? Not L1 or anything like that, right? Like the Hilbert space kind of thing projection. That's what this is about. Yeah, you can even define the inner product, right? Inner product would be covariance kind of thing, but you have to kind of be careful to subtract the mean because yeah. But yeah, you can define the whole Hilbert space structure out of this. All right. So now, sadly enough, right? This is a very nice framework to think about things because everyone knows about mean square error and via regression, like econometrics, like you said. Except that it's not going to help us here because trying to prove that something is the best mean square estimate is right. So basically, right, at least let me tell you, this gives you something to go with, meaning that you know what this guy is because it's on the E, right, on the P side, you know what it is. So if you really want to use this framework, you just have to show that somehow this guy is the best mean square estimate in the P tilde sense of X, right? The reason why, so it's already in FT, right? So everything here is in FT, so that's fine, F little t. The only thing you have to prove is that it's the best estimate of X in the P tilde sense. But yeah, that's painful, right? So there's an alternative way, which is less intuitive, but equivalently, all right? This is the definition that you will see in a measured theoretic course. Conditional expectation of X, right, given Ft, let's still call it Y, okay? Such that for any Z in Ft, the inner product between X and, inner product of Y and Z is the same as inner product of X and Z. This actually exactly translates to the above, meaning the best mean square estimate. But this is easier because it gives you a direct calculation to verify. By the way, right, I keep saying about projection, it actually has that sense, right? So here's your Ft like this. X is something like this. Again, right, don't take this literally, but it really has that taste, right? So think about your projection, right? If you do orthogonal projection, right? So this right here would exactly be your good old conditional expectation. So what we're saying, right? We're saying that for any other vector in this space, this is Z right here. And when you take the inner product of these two guys, inner product between X and Z is the same as inner product between this and this, which if you know your projection is true, because when you do projection of X on Z, right, what you're doing is, when you take the inner product, right, you are really projecting X on Z, but that's the same as first projecting X onto the space that Z belongs to, and then now do that projection on Z, right? So it's like that. Okay, so that's the characterization. But it's easier because you use the inner product framework, so it allows you to do calculation. But like if you are not sure what this means, then it really is confusing, right? Y, Z, X, Z, can I do X, Y in here, that kind of thing, right? The answer is no. You're doing projection of X on Z, and you're doing projection Y on Z, right? Y meaning your proposed conditional expectation, and they have to be equal. And the reason is this picture. All right. Question? Okay, so now, right, let's take it home. Well, not yet, but almost. So, right, so what we're proposing? We're still proposing this framework of conditional expectation, right? Which is this divided by this. Okay. And so following, right, this definition, what I need to show is that for any, right, Z in FT, right? Right, so this is my Y, right? This is my Y, right? This is exactly Y. So I want, this is my X, right? So E tilde of X times Z is equal to X E tilde of this nasty piece. It's just hard to write down. Okay. Now, if I can show this, then I have this. Any questions so far? Oh, you know what? There's one hiccup, right? The hiccup is this Z may be confusing with this ZT I use. So maybe let me try that with U, right, to distinguish that. Okay. All right. Does anyone see how we can prove this? Actually, it's almost very easy, right? Is it? How can we show something like this? Well, you know, actually you have no choice but do some calculation. And usually, right, you want to do from the more complicated side, right? And because you can simplify stuff, right, to the easy side. So let's take the right-hand side, right? What can you do? Well, this is now properly an expectation. So you can convert it back to E, right? First of all, you can convert it back to E. So I won't write the right-hand side, but if you convert it back to E, right, then you have this. Right? So to go from E tilde to E, right, what it causes multiplication by Z. Yes. Now, what can you do with this? Don't forget, right? U is F little t adapted. So it actually is known by FT. So in fact, right, what you can do is you can tuck that inside the expectation is a constant. All right, because U is adapted. No, U is inside the sigma algebra. Right? U is inside the sigma algebra. All right, now what can you do? Again, right, it's very tempting in the sense of what you see conditional station here, right? The good old trick of conditioning and then not conditioning, right, will be good. So I'll, in the interest of, you know, not writing too much, I'll do this, right? The dot 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 is that thing inside. This is a whole dot dot dot. Okay, so basically I just do the time honor trick of conditioning and then not conditioning, right? But right, notice, you know, just observe, right? Because otherwise writing it down is just painful. What do I get by conditioning? When I condition, right, then everything that is already conditioned is a constant, right? So this dot 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 here, these guys will factor out of the dot dot dot, right? So I will have something, so the fraction, right, will factor out of dot dot, or maybe I do this. The conditioning, right, will factor out, leaving me with what? Z big T. right? But of course, these guys cancel, and then it will neutralize this conditioning, leaving me with this. But what is this? Now I can convert it back to the tilde world, which is exactly that. Any question? We're good? All right. So what this is known for is called a conditional change of measure formula, right? Conditional change of measure formula. Now, be very careful here, right? That Fatima said is Z little t, because I guess she used this framework. But it doesn't have to be that way, meaning that, right? The Z big T here, indeed, right, is a martingale and stuff like that. So it's very suggestive. But you shouldn't really, how to say this, right? The reason why I don't encourage that is it may run into some issue. Basically, that this is still hold, right? As long as you have the change of measure defined instead of Z big T, you call it Y, right? So you can really define a process like this out of it. But you should really think of Z big T now, it's just a random variable, right? As a random variable. What happens is that, pedantically, now you define, right? Now you define Z little t, right, as expectation of Z big T, condition Ft, right, which for all we know is just this. Sorry, theta, right? All right. And so now we can conclude that Zt is a martingale, is a P martingale. All right. And so now, right, we can back to our problem. Now we can show, right? That W tilde, right, which is W plus theta, is a P tilde martingale. Sorry, is a P tilde prime motion. All right. How do we do this? Well, again, right, remember what we want to show is conditional expectation of this lovely exponential. Right, is exactly itself, but at time little t, right? Oh, by the way, right, here's something funny to pay attention to as well. It might be very easy to confuse this change of measure kernel with the martingale characterization, right? Which actually there's some deep connection there, except that there's a little minus sign here, all right? This minus sign here plays a super important role. If you have it to a plus sign, the result is wrong. In fact, if you change it to a plus sign, guess what? Then this must be a minus, all right? If you have a plus sign like this, then it must be a minus. So it's very, very important that we have the framework right, okay? It's a minus here, so it's a plus here. Because, right, what the drift, you will have the wrong sign if you use the wrong change of measure kernel, right? So anyway, right, so let's compute this. So by our discussion above, right, this will be, right, so E of this exponential, right, let's just multiply by Z big T, right, and then divided by Z little t, right? So now we can do it, okay? So because this divided by this. All right, so now let's take a look at what this guy on top is, right? The bottom is just Z little t. What about on top? Well, now you have to unravel, right, what this ZT is. But right, when all the dust settles, basically, first of all, right, you have also unraveled the W tilde, right? So W tilde, so let's just analyze the top, right? The top piece. The top piece has expectation of, right, sigma of W big T plus theta times T, right? And then minus 1/2, sorry, so this close parenthesis, minus 1/2 sigma squared T, and then times, right, exponential of minus theta T minus theta WT minus 1/2 theta squared times T. All right, like that. So what does that give us, right? That gives us that combining, right? Combining sigma, right? Combining WT, right? Combining W big T. Combining W big T gives us sigma minus theta, right? Times W big T, right? And then, right, notice that these square terms and this interaction, right, exactly is e to the minus 1/2 sigma minus theta squared times T. You agree? Right, because if you factor out a minus 1/2, then you got a 2 sigma times theta. Then, right, what is this? Well, it turns out, right, that actually this is going to be exactly this expectation, right? So the top actually is going to be 1. So this expression actually is just 1 by this calculation. Question so far? So, right, amazingly enough, this conditional expectation is just 1 over z little t. So to continue, right, it's going to be equal to one over zt, right? So it's e to the plus theta. Yes, oh, sorry, theta squared, right? Oh, I'm in trouble here, right? Am I? I am in trouble. Did I do something wrong in the calculation above? Because there's no sigma left. There's no sigma left. Anyone see something wrong here? So the top should not be 1, I think. Yes. How could I forget that? Thank you. Thank you, thank you, thank you. Ah, so silly. Yes, you're right. So actually, I still need conditioning. Appreciate it. So here, right, this whole thing still conditioned on F little t. What that means is this is conditioned on F little t, right? So actually the top is not 1, but the top is so conditioned on F little t, right? That would be so E to the sigma minus theta times WT, right? And then you have the minus 1/2 sigma squared, which would be a martingale. So that would be E to the 1/2 sigma minus theta squared, like this, right? The reason is because, hold on. Let me try to think. You know what? I'm silly, right? I should put everything here in conditional notation, like this. And then because this is a martingale now, so I'll get this. All right, so that's the top. Is that okay? All right. Yeah, this calculation, it'll work out. It's just, painful to track the detail. Oh, shoot, I'm out of time. All right, let me finish this real quick, right? So basically what we have is, right, so continue, then we got this, right? Divided by ZT, which is multiplied by E to the theta WT, right? Plus 1/2 theta squared times T, right? That's divided by ZT, right? So the top is this. So I will do that. And you see, right? This one beautifully cancel out. So I'll get E, right, to the sigma WT. I'm still having a cross term left. Gosh, I messed up again, right? So it's supposed to be this. But I still have a cross term left because between this and this, right? I still have a sigma times theta. So I'm not home. There's still something wrong about this calculation. Yeah, I missed something up here. Sorry about that. Okay, so maybe let me write down this calculation in a LaTeX and send you. It will work out, right? It just, I think I missed something again somewhere there. Sorry about that. All right, maybe let me take a look and now I'll send you a LaTeX file for this detailed calculation. Not super important, but yeah. Okay, so maybe let us stop here. Any questions about anything? So that's still not working. I still miss something. Question? Okay, then if not, I'll see you on Monday. All right.
Can I ask a quick question on the homework?
Go for it. Yeah, thank you.
So for question 5, I started it too late and I don't have enough time to get 2 data points for different days, but I found on NASDAQ that they actually, if you give them your call, the date of expiration and the strike, it will give you a lot of the Greeks. So can I compare my theoretical Greek value with what NASDAQ gives?
Yeah, that also works. That's one way, right? You don't have to stick with our, again, right? Yahoo Finance is just one way to get data. That's one way you can do that. I just want you to compare with some empirical, calculation. But here's the thing, right? I just came up with that idea of daily data because I thought that Yahoo Finance can give you historical value, right? But if you want 2 data points, right? Why not run it 1 hour apart? That's also one way, right? Because the point is what? Your delta, right, is just a change in the option price when the stock price has moved. So as long as you observe 2 data points where, right, doesn't matter how short or how long, right? that the stock price has moved, and that result in an option price move, right? In fact, actually, it's better to do it within 1 day, even 1 hour apart, right? If you record, you know what I mean? Then you will have a movement of a stock, and then you will have a movement of option price. Does that make sense? The contrast with the Nasdaq data is that I haven't looked at it, so I don't know. But do they have like, is that like a daily delta that they output, or is it like minute to minute delta output, right? This when it comes to data, right, it is actually a jungle, meaning that it depends on how people calculate it. You know what I mean? So I'm not saying that it's wrong for you to calculate with Nasdaq, but what I want like you guys to understand is how is the number calculated, right? From whatever vendor, right? That's actually the issue you have to deal with when you practice, right? How are they calculated? How do you calculate yours? And hence, right, what's the gap? Does that make sense? Does a gap come from the model, or does a gap just comes from you guys? I mean, different people using different data points, different calibration. Does that make sense? That's more of what my interest. If you can find some reasonable way to do it, right? Then you know, go ahead. Does that make sense?
Yeah, that makes sense. Thank you.
Sure.
Well, I also had, if no one else has a question, can I ask something specific about like my code for homework for question 4? Something that like
you want to share your code?
Yeah, if I can.
Sure, go ahead.
So I'm not sure why, but for my 4C, when I try and get like a price path using the differential formula, and I compare it to the direct formula, it like starts off really similar, and then it kind of just like diverges. But the weird thing is, like, if I rerun it, like sometimes it would be almost perfect, like it would like stick to the, but then other times it diverges, and I've been looking at it for like almost 2 days now. I just can't figure out what it is.
That's something nice that you've discovered. You could report that, right? Again, I'm not looking for a perfect answer, right? I'm looking for understanding. So do you mind running it again? How long does it take you to run it? Run it again.
No, it doesn't.
It always diverges though. So can you zoom out a little bit? I have a hard time looking at your code.
Oh yeah, I was zooming.
Okay. Now, so go down. So the top is differential and the bottom is direct. So first of all, you should notice if there's any consistent trend. Is it always that the direct is below the differential formula?
Yeah, that's one of the things. Like I think when the price is 0, like my direct formula will like go to 0, but my differential formula will kind of level off at something a little higher than 0.
Now the differential formula, right? You got to execute right, and the left point and the right point might matter. So sometimes you may accidentally use the right point without knowing it. Okay, that's one thing I can think of. So go back to your differential formula, right? How do you do it? S is.
So S underscore T, that's I just generated it from here.
Yeah.
And then so this is T1 is basically all the terms associated with DT, and then term T2 is all the terms associated with the change in the Brownian motion icon.
Yeah.
And the Brownian motion DW, I defined it as over here. So it's basically taking.
So do me a favor, and just out of silliness, can you try, instead of WTI, you do WTI plus 1?
Yeah, I might run the thing might not run out of the index might not work.
So shift the index back to -2 or something, right?
Like that.
Yeah, it's just some silly fix, but
Yeah, so
ouch.
this is what I think.
Oh, wow. Run again. No, that's not the right one, huh? Okay, so shift it back then. So the next question is your Greek correct? I saw that you input delta t in there. What's delta t?
Delta T, that's so the line space.
Oh, that's just a time, right? You call delta.
Yeah.
It's a time.
Oh yeah, it's the time.
It's just a time. All right. And I assume your formula is correct.
Yeah, I looked over it like 100 times.
Also, were you careful to use the right f sub t? Because like I said, right, the f sub t and the theta is negative each other.
F sub T, yeah. So
No, so
the stable.
that's your quote, right, from Wikipedia, right?
But on Wikipedia, it's negative. It's like negative T1 minus.
Oh, so you already negate already there.
Yeah, I did that already.
Oh, I see. Okay, right. Okay, so you already did that. Okay. What about tau? Is tau you define tau correctly, which is t minus little t?
Yeah. So when
Tau will move, right? Tau will move. Oh, so when you do delta t, that yes.
Yeah, that's my tau. Yeah.
You sure? Because so you know I mean, like the formula for these guys will depend on tau, which is big T minus small t, right? It's not directly depending on little t exactly. I think it depends on tau. It doesn't depend on big little t, right? Did you make sure you do that correctly?
Yeah, so that's why I define delta t like starting from tau. So tau here is initialized to 50, and then so it starts from there and then it goes to 0. So like when little t is equal to 0, that's when we have like
Oh, so you count it backward.
Yeah.
I see. Okay, I see. Yeah, I see what you mean. Yes. So I see. That's why you define like that. I see. So f sub t dt f sub xx 1/2 sigma square st f sub x r st.
Now, one of the things I was thinking about is I'm sure like all these runtime error divide by zeros will cause problems.
Yeah, where does that come from?
So I'm pretty sure it comes from the fact that when tau is approaching 0, like here we're dividing like
I see. So right, so the Greek is not defined, right, when tau goes to 0, right? So maybe you should really not include the last point, but it start diverging even before that, right? So I don't think that was the issue. You see what I mean? Your graph diverged before that, right? It's only the last point. Is that right? You know what I mean?
Yeah.
So, I mean, like there will be some issue with the Greeks at the end, but I don't think. You know what? First of all, right? Suppress your sigma. Let sigma be 0, and see if you graph it and see what happens. Okay, that works. Okay, so now so turn on a sigma, but maybe try what so Yeah, no, just 0.1, whatever, right? But let R be sigma square, right? 1/2 sigma square, so that we will only graph the Bragg motion side, right? So let's try to see if it is a drift that matters or not. You know, R, so you define R as 1/2 sigma square, right? So maybe you want to shift down or something. Oh yeah, you can do that. Yeah.
Okay.
Yeah, you can do that. Yeah, 1/2 sigma square. Yeah. So here, right, if you do it right, so try to output your T1. I mean, a little bit. If this calculation is right, the T1 must be 0, right? Because we're only graphing T2. Do you agree?
Yeah,
So
so
try to print T1 or something. It will be nasty, but reduce the n a little bit to 100 or so. Yeah, you see. Yeah,
yeah, they're not zero.
it's not 0, right?
Mm-hmm.
That's the issue, isn't it?
Mm-hmm.
Oh, hold on. No, your T1 is not 0 because you also include the f sub x. Wait, hold on. What's the Black-Scholes PD? F sub t. Sorry, I'm trying to recall. The Black-Scholes PD should say f sub t. Gosh, for some reason, v sub t minus rx. Oh, hold on. Oh, no, it should not be 0 because you're right. There's a r component there. So that's not 0. You're right. It should be exactly r. No, it's not 0. It's not 0. It's r minus r times that. So I think you're fine. It's not 0. It's by Black-Scholes formula is r times s. It's r times s. So try to print r times sti and see if that's right. Print also another line,
So print,
r times sti.
I'll just do it outside.
No, you can't, because it should
Oh,
be
for each, yeah.
for each point. Yeah. R times sti. S sub t. Are they close?
Yeah, they're pretty close. So it's like the
Okay,
first
so
two.
right, that doesn't seem to be the problem either.
We actually here it's changes. So here T1 is 0.05 and then R times
Right, and
STI.
that small gap can really cause trouble, right?
Yeah.
You know what, where I got that from, right? It's actually a Black-Scholes PD. These Greeks must connect with each other, you know, in the right way. Oh, you know what? It's actually not STI. It's the call option price, actually. So it's not. Do you have a call option price? It's not STI. Sorry, it's CT.
Yeah.
You have the call option price, but it's not C. Yeah, exactly that. Wait, hold on, Kareem. Let me try to think, because you're plugging in the Greeks minus RV plus the Greek RS. Yeah, it's call option price, right? Okay, try again. Wow, even worse. What am I thinking? It should be R times B, right? I mean, it's the Greek plus R f sub t plus f sub x plus 1/2 sigma square s square. Yeah, it should be the Greek. It should be R times the, sorry, it should be R times the auction price. So yeah, something is off with that. You know what? Can you comment out the T1 and comment out a print? Just comment it, you know, sharp, yeah, comment out a print. Now do something silly here. Let the T1 be that quantity R times something. So coming out a second print too.
Okay.
Let T1 be R times that, you know. See if it See if it works.
Oh,
You have to comment everything out. The second two lines on the T1. The second two lines on the T1. No, on top. You didn't comment. Go to the first comment. Go to the first comment. No, above. Yeah, the second line and the third line, right? You have to comment them out too.
yeah.
What the heck? So the change in the option price. Is the delta plus oh, should it be DT Kareem? DT, right? T1, we forgot to multiply with DT, right?
Oh, yes. Oh, yeah, that's better.
Try again. Yep. Something in your Greek is wrong.
My Greeks?
Yeah, right? Because you see how I just demonstrated, right? So the differential code is not wrong. Yes?
Mm-hmm.
Because I just demonstrated it. When I change the T1 to what it's supposed to be,
Mm-hmm.
and you got it. So that, and you know where I picked it up from, right? The Black-Scholes PD. We'll talk about it later, but I think you know what it is. Basically, the Greeks adding up like that must be equal to R times the option price. Okay? The fact that you didn't get the differential thing worked out, meaning that something in your Greek did not come out right.
Yeah.
So I don't know. You know what? Maybe I'm silly here. Maybe the theta is supposed to be right. Maybe I just tell you guys the wrong thing. Can you try just minus FT?
Minus FT.
Yeah. It could be that somehow you know, that's sometimes the most obvious error. Yeah, okay, try that. Fuck.
Oh, wow.
What? Oh, I shouldn't curse when it's still recorded. That's weird, huh? So you fix it, right? So I told you.
It works now.
I told you guys the wrong thing. I mean, I fixed you fixed the sign. Wait, so Wikipedia already took the minus sign into account? God dang it. I just said the wrong thing then. So Wikipedia already took the minus sign into account, I think. You know what I mean?
Yeah.
So theta is really defined as minus partial with respect to tau. It's not partial with respect to tau. Oh, yeah. So I don't know. I mean, look back into Wikipedia. I guess somehow I said the wrong thing, but yeah. So you were careful, but that hurts.
Okay.
Does that help?
Yeah, that helps a lot. Thank you.
Okay, sure. Yeah, I know that usually the problem comes with how people define the theta. You know, for me, I don't care, right? But it does mess up your formula if you don't use the right one.
Right,
Okay.
Thank you.
Okay, cool. All right, so I'll see you then.
Yeah, we have a seminar today, right?
No, sorry, next Thursday. Sorry, next Thursday, the 3rd, right? Did I write the time? It's the Thursday, right?
I remember it was a Thursday, but I forget. Okay, so next.
Yeah. It's March 3rd. Yeah, every 2 weeks. Yeah.
Thank you.
Okay, cool. See you. Oh, thank you for teammate. So what was wrong? What did I do wrong? Yeah, it's kind of annoying. So why does it not? It doesn't seem to simplify, right? Because it should be the result. You know what I mean? So it should simplify, right? So it'll be good. Then I'm not super embarrassed with what did I do wrong? I mean, not what did I not see? Because you see, I don't think this simplified to that, right? Because there's this quantity and I'm supposed to only get this, right? So what about a cross term? What happened? Oh God. Right. See, I'm a victim of what I said. Right. The confusion between W and W tilde. Oh gosh. Right. Dang it. Thank you. Thank you. Thank you for checking that. So I'm good, except it should be W tilde. Appreciate it. All right, cool. So I'll just gonna show the kids this next time. Appreciate it. Okay. So I hope you enjoy the lecture so far. All right, so Monday, right? The kids will have an exam, so we won't have a lecture. All right, we'll continue lecturing. Next Thursday, right? All right, cool. See you. You too.